So let me write this. E of xy, without calling it a name, without giving a name to xy, this is called the correlation of x and y. I am sure you people have used the word correlation in some other context, but the E of xy is a precise mathematical terminology for is a meaning of correlation, right. So this obviously is a special case of this, where I am going to stick in here the product xy or here. Now, okay, fine, yes, I have xy, but can it simplify? In general, this right, you cannot simplify that sum or that integral, the double sum or the double integral. You can simplify only in the case that this joint is a product of the marginals, i.e. x and y are independent. So when x and y are independent, I am going to use right at the bottom here, I am hoping that whatever I write at the bottom here is fully recordable without any. So when x and y are independent, what can you say about exy? This implies what? This becomes pxx into pyy, fxx fyy, and then you get, and then this will always be a rectangular grid, this will always be a rectangular region. So you can always integrate over y alone and x alone. So what happens to exy? Right. This implies that this correlation is a product of the means. So this is an implication which goes only in this direction for now, right. Do not, as I will show you not too far, maybe latest by tomorrow, this does not imply independence. It only, this implication for now goes only in this direction. Let us not take right, I am looking at the most general thing, right, not taking specific examples, right. So we are now just looking at general independent x and y only, or not independent, right. When they are not independent, in general this is not true. But the independence case can be stretched even more. We already pointed out that if x and y are independent, g of x and h of y are also independent. So you can say one more thing, right. What can you say for independent xy? This E of gx multiplied by hy, remember this g is not the same as this g because this is a function of two variables here, so, but I do not want to keep on inventing subscripts and so on. So what is this going to be? Gx and hy are independent, as we already pointed out, for when x and y are independent. So this is going to be, again, it depends only on the marginal statistics of x and y. So this will be E of g multiplied by, again this lotus principle comes in, right, is just use left and right in all of this. And notice the way, just one E for everything. It is absolutely unambiguous because you look at this and say, this is E of g of x, it uses only the PDF of x, finished. This is E of, there is a x here, y here, but so it has to in general use the joint PDF or joint PMF, right. Is this clear to everybody? Okay. So this is a correlation. Now why is this correlation so important in the variance calculation of the sum? If you go back to, okay, so I will draw a line here. So I will say back to, now I will put z equal to x plus y. Now I want to call it a name, Z. Here, same thing. So what is E of Z squared? Remember, we are only dealing with numbers, random variables are after all numbers, right? So algebra always applies. Z squared is x plus y whole squared, which is x squared plus, surprise surprise, is x squared plus 2xy plus y squared, right? 7th standard identity brought back to use in the form of random variables. Any problem? Okay, now linearity again. What version of linearity should I use? I in fact I didn't, so now we have what you might think of as different functions of x and y in general. Not exactly this kind, this involves many different random variables. Actually I wanted to write something like this. I put ai of g I of x comma y, but ended up somebody said linearity and I got sidetracked and put many random variables, but that's okay, there's nothing wrong with this, right? But I mainly what I wanted to put here is ai gi of x comma y, again the same kind of thing here. So this is E. Now you see how it simplifies, right? So this first term depends only on the marginal PDF of x. The third term depends only on the marginal PDF of y. But this term here is exactly this, E of xy. I am not assuming independence, I am assuming just this. Please don't throw any independence, there is no independence right as of now. Okay. Now, okay, so what is, so how do, but variance is not just this, right? Variance, this is minus what? Which is what? What is E of z the whole square? From here, it is E of x the whole squared plus 2 Ex times Ey, right, plus E of y the whole squared. Correct? So now if I take the difference, what do I get? I think I can go back here. Sigma, the variance of z. By the way, the sigma z squared is a bit inconvenient to write down. Another notation we are going to use for variance is to write VAR and put the name of the random variable within brackets, which is is some ways cleaner because it avoids subscript, and the square also. Superscript and subscript are both avoided in this quasi English mathematical notation, right? But it's fine. So this is basically just E of z the whole squared minus the mean squared, which is that, which is what? This is sigma x squared plus sigma y squared, we will write at the end. What is the term in the middle? The term in the middle is called the covariance of, the twice covariance of x comma y. So if I write this as 2COV x comma y, what is that covariance of x? Where this covariance of x comma y is what? Tell me. It's the expectation of xy minus or mx my. right. So, this is the formula for the variance of the sum. If I took the difference instead of the sum, what would be the variance of xy, x minus, so what would be the resulting variance? If I wanted to write, now look at the power of this notation, I can just simply write variance of x minus y. I do not have to give it a name u or v or anything, I can just simply write like this. This will be, turns out again these two will come always with a positive sign, this term alone will become negative. Please go back, do the derivation, you will see only this term becomes a minus. So, this becomes sigma x squared minus 2 covariance xy plus sigma y squared. So, using this covariance idea, you can write out not only the sum, the variance of the sum, but also the variance of the difference. Supposing x and y are independent, now we will bring in independence. Then if x and y are independent, then covariance is always 0. If this covariance is 0, then the variance of the sum is equal to the sum of the two variances. The variance of the difference is also equal to the sum of the two variances. In fact, the last thing I want to say for today is whether or not x and y are independent, right, if their covariance is 0, the x and y, the covariance can be 0 independent or regardless of the independence of x and y. Note that, just last thing, because I started exactly 15 minutes ago, I need my full 50 minutes, right. So, last thing. So this in general does not imply that x and y are independent. Covariance xy can be 0 without x and y being independent in general. All it says is covariance x of 0 is the only thing it says is that if this covariance is 0, it only means this, E of xy equal to Ex into Ey. This is the only thing that it means. And there is a special term for this, x and y are called what? Uncorrelated. Okay, so we will stop here.